So now, usually after introducing Maxwell's equations, pretty much the foundation of electromagnetism, and again, as I told you, once you have those equations, you should be able to describe any phenomena in electromagnetic phenomena in the universe. And optics is just one of the electromagnetic phenomena, right? So basically, you can think it's first we thought that there is a separate world of electricity, separate world of magnetism, but actually they unite. It's just a one world of electromagnetism. And now they're getting greedy, and now they annexing the world of optics. Actually, optics is also just a part of electromagnetism, right? So now after this, of course, we're supposed to. Tomorrow we will discuss. We will play a little bit with Maxwell's equations in order to get electromagnetic waves, right? Which is basically light, right? And so, in order to start tomorrow, continue tomorrow, discussing those waves, we need to be familiar with traveling wave equations. So at this point, I usually sort of digress a little bit. It's a volume 1, chapter 16, and we spent usually one class playing with traveling waves. And I asked you either to watch the video which I recorded a year ago, or read my notes, right, as a preparation, because I don't want to spend additional hour discussing that. But now it's actually, this method is called flipping the classroom, right? I think it's called, or turning inside out, whatever. So when your students learn by themselves at home and then you just practice it in the class, right? I'm not a big fan of that approach, but here I use it, right? But only once. So, first of all, what is a traveling wave? Let me just discuss key points, right? And then we will start looking at the examples. Key points. First of all, what is a wave? Wave, it's a disturbance which propagates. If I take this chord right now, there is no disturbance, right? So right now this chord is in the equilibrium. But if I displace it, if I create, for example, this disturbance, right, I created disturbance, and if I release it, of course, it will start traveling in that direction and that direction. So I create disturbance, and it starts propagating through your medium. So I created the wave, right? Of course, there are two types of waves: longitudinal and transverse. This is an example of a transverse wave. Pretty much particles, you see, move perpendicular to the direction of wave propagation. Wave propagates in that way. Particle gets displaced. Particles are displaced in the perpendicular direction. Transverse wave. Electromagnetic wave is an example of a transverse wave. Right, then both of these waves, longitudinal, transverse, actually any waves, can be explained using a traveling wave equation. Right, and that's basically, I spent that video and those notes just introducing this equation. So, but let's just quickly analyze it. No, not analyze it, discuss it, right? And then examples. So first of all, why? Let's start from the left and move all the way to that side. Why? It's a displacement of particles of the medium. So what do I mean by that? Again, the same chord, wave propagates that way, right? But let's look at this particle. What does this particle do in life? What's it like? It just moves up and down, up and down. Particles do not travel. They just move up and down, but wave propagates, right? So pretty much this Y, sometimes instead of Y, capital letter D is used, displacement, right? Basically, it's a displacement of this, for example, knot from this equilibrium position. For example, gets displaced by 1 centimeter, 2 centimeters, 3 centimeters. That's what Y is, or D sometimes, right? So it's a displacement from the equilibrium. That's what Y is, right? Then this wave, it's a function of two variables, x and time. X, it tells us along which axis this wave propagates. So in this case, x is along this chord, right? So if I align x along this chord, so this x tells us that our wave propagates along x-axis. If, for example, z-axis was along this chord, then of course I would have to put here z, right? If y was along this, right, so then I would use y, right? So this variable tells us along which wave propagates. Then time, yeah, it's a time. Right, so then this wave lives in two worlds. Spatial world, it depends on x, and it lives in temporal world. It depends on time. So all these quantities which I'm going to introduce, we're going to divide into two categories. Spatial quantities, basically which describes the life, which describe life, a life of the wave in space, and temporal quantities, which describe life, a life of a wave in time, right? So let me first call x. It's a basically spatial variable. So here I can write, so it's a x, it's a spatial variable, right? And t time, it's a temporal variable. Okay, I will use blue for everywhere. It's a temporal variable. So you see, I already started using this adjective, spatial, temporal, right? Okay, so then equal A. A is the amplitude. Okay, usually students don't have any troubles understanding that. It's just a maximum displacement over particle from the equilibrium, right? So this particle, let's say maximum displacement is 5 centimeters. Okay, so amplitude is 5 centimeters from the equilibrium, measured from the equilibrium. Not from this minimum to that maximum, no, from the equilibrium to the maximum displacement. That's what amplitude is. All right. Then we have periodic function sine. Sometimes instead of sine, you can see cosine function. But what's the difference? What's the difference between sine and cosine? Both of them are periodic, right? And the only difference, how can we get, for example, cosine function out of sine function? We just need to grab sine function and shift it by pi over 2 along x-axis, and you will get cosine function, right? So pretty much the difference only in this initial phase. But you see, I'm just telling you, if you see cosine function over here, don't be scared or terrified, right? It's just a slightly different way of describing it. So what do we have inside of periodic this function? So first of all, this construction, this whole construction is called the phase of the wave. Anyone who is going to work in optics, you're going to use this word phase of the wave a lot, right? Especially in low frequency, right? So this is called the phase of the wave. And you see, there are two variables, right? Spatial and temporal variable under the sign of this periodic function. It means what? It means that our wave is going to be periodic in both x and time. So it's going to be periodic in space, and it's going to be periodic in time as well at the same time. So if this wave is periodic in space and time, of course, we need to introduce the proper quantity describing this periodicity in space and time. All right. So first of all, let's introduce periodicity in space. So what is that periodicity in space? It's effectively a distance, right, over which wave is going to reproduce itself. So the wave is going to look exactly like what that distance ago behind, right? So it's a distance over which wave reproduces itself. What's the term for that? Most everyone knows that. It's a wavelength. Wavelength, it's a distance over which wave reproduces itself. It's a basically spatial periodicity. The name is wavelength. The meaning of that is a spatial periodicity. It's sort of like, I know, the student, right? His name is John. So the name is John, but what's his nature? Human being, right? So the same here. Name wavelengths, nature, spatial periodicity. Right. Okay, so symbol lambda. Pretty much everyone uses lambda. First I will write its name, wavelength, and then the meaning is spatial periodicity. Spatial periodicity. But you can see actually, since it's in the first row, so it's a spatial periodicity, so it's a spatial periodicity, right? Then we need to introduce something similar for the temporal world, right? Since there is a time inside of this periodic function, so it means that wave is periodic in time. So now we need to introduce a temporal periodicity parameter which describes a periodicity of the wave in time. So what is that? Again, most of you know that it's the period. Period, it's a stretch of time or period of time over which wave reproduces itself. So you see, wavelengths, it's a distance, stretch of, it's a distance over which wave reproduces itself. Period, it's a time over which wave reproduces itself. You see, exactly the same, we just need to replace space with time. So, and of course now, the name of this quantity, it's a period. Capital T, the name is period, and the meaning is temporal periodicity. Temporal periodicity. Right. Okay, so now we know how we can describe periodicity. Then next, what about frequency? Basically, how fast a wave oscillates, right? But now, since we have periodicity in space and time, so we should introduce how fast we need to introduce parameters which would describe how fast wave oscillates in space and also how fast wave oscillates in time. Right? So we need to introduce frequency basically in space and frequency in time. And of course, the definition of both quantities will be very similar. So first, for the spatial frequency, it's a wave number. Most of you never heard about this term. Some of you might heard, but usually no. So K, wave number, by definition, is introduced by 2 pi divided by wavelength. So basically, you see how we introduce it. 2 pi radians divided by spatial periodicity, wave number. It's a very, very common, used a lot term, especially in low frequency optics, right? When I was working on my PhD project, so yeah, we used it almost every day, right? And lots of spectrometers, if you look at the spectrum, right, which they produce, for example, intensity of, I don't know, some source, right, versus frequency, intensity of, some source, or maybe absorption. And usually by default, spectrometer plots versus wave number. Of course, you can change it, but usually by default versus wave number, right? So this is wave number. Okay, so the name is wave number, and the meaning is just a spatial frequency. Basically, it's a meaning is how many cycles a wave can make, for example, in 1 meter. But of course, here it's scaled to 2 pi, 2 pi radians. So how many cycles in the unit of length? Spatial frequency. Okay, so let me write. It's a name wave number. Wave number, meaning spatial frequency. Spatial frequency. Right. You know what? Let me frame this because it's a, for most of you, you see it for the first time, this wave number. So introduce it as 2 pi divided by the wavelength. Now, what about temporal frequency? Okay, most of you are familiar with the term. It's just a regular frequency. And it, oh, no, angular frequency. Here we need to introduce angular frequency. So, and introduce it, we introduce it in, you see, in a very similar way like what we like how we introduced wave number. Look, we introduce wave number as 2 pi divided by spatial periodicity, lambda. So guess how should we introduce this angular frequency? 2 pi divided by the temporal periodicity in exactly the same way. So it will be 2 pi divided by period. So name angular frequency, angular frequency. Yeah, correct. And the meaning of that is just the temporal frequency, right? Meaning temporal frequency again. So temporal frequency, right? Maybe I should frame it also since I framed that. So again, that's how we introduce it by definition. And so what? We have this wave number over here, spatial frequency times spatial variable, and then temporal frequency times temporal variable. So pretty much all information, all spatial information about the wave is hidden inside of this term. All temporal information about the wave is hidden inside of this term omega t. Okay, so pretty much now we're at this point. We introduced all this. Now phi naught, it's the initial phase. It's a basically constant. If a wave is given constant, that initial phase is a given constant, right? So which shifts the wave along the direction of propagation, in this case along x-axis. So if you add this constant, it just shifts the wave either in the positive x direction or negative x direction. It's sort of like when I told you about the difference between sine and cosine function. What's the difference between them? Pi over 2. So if you shift with this phi naught, right, if I add here a phi naught, let's say equals to pi over 2, then I can write it in terms of cosine function. You remember high school stuff, right? So initial phase. Then, of course, wave travels, propagates, either in this case positive x direction or negative x direction. So how should we get that information from the equation? So minus this minus, if you see minus, it means that the wave propagates in the positive x direction. You see, we have reverse situation. So minus give us propagation in the positive x direction. So let me write it travels in plus x direction. And plus means that it travels in minus x direction. Right. So remember this sort of inverted situation. Minus give us positive x direction of propagation, and plus give us a negative x direction of propagation, right? So you just need to remember that, right? So what else is missing in our description? Again, wave propagates. It means that we can, of course, ask the question, how fast it propagates? What about its speed? Absolutely logical, normal question, right? And you see, up to this point, every time I divide quantities into two categories, spatial, temporal. What about the speed? Speed is neither of those. It's neither spatial nor temporal, because what do we need to know in order to find the speed? For example, like in physics 1 or in high school, right, or middle school, whatever you used it. For example, you want to find the speed of an object. What do you use? You take distance, spatial quantity, and divide it by the travel time, temporal quantity. So you see, you're mixing spatial quantities or parameters with temporal parameters in order to find the speed. Exactly the same story here. In order to find speed of the wave, we need to mix spatial and temporal quantities. And in my video and in my slides, I sort of proved, I derived that speed. Okay, let me write underneath speed. Okay, v. We can find it, as I said, again, by mixing spatial and temporal quantities. So you need to take omega, which is temporal frequency, and divided it by the spatial frequency, right? Temporal quantity over spatial quantity. So that's how we can find speed, omega divided by k. So it's one way of finding speed. If you forgot, you can check the units. Omega, it's a radians per second. K, okay, actually I forgot about to emphasize that k wave number has units of 1 over meters or 1 over centimeters, right? So here radians per second, here radians over meters. So meters goes upstairs, second goes downstairs. We have meters over second, meters per second. So correct units of speed. So then How else can we calculate this? Omega, this is the definition of omega, right? 2 pi divided by t, you can plug it here. And then k is 2 pi over lambda, you can plug it there. So if you arrange them quickly, you can get also, let me just write it, v equals lambda over t. So it's the second way of finding. Or since we know that regular frequency is a reciprocal of the period, we can write it as lambda times f. So these are two ways of finding speed of the wave, right? So this, and you know what, let me write it in this way. Also this quite often. So you see, we're mixing temporal and spatial quantities. In this case, a temporal spatial periodicity versus temporal periodicity. Temporal frequency versus spatial frequency. Right. Okay, what else I need to mention? No, that's it. That's it, right? Okay, so now I think it's time for us to start looking at actual problems. Again, let me still check if I mention everything. Yeah, looks like. Okay, so the next then problem 14 is a chapter 16. It's a volume 1. It's a volume 1.
Professor, I can't hear you.
As I said, it's from a volume 1, right? Chapter 16, volume 1. If you do have volume 1 from physics 1, great, right? But if you don't have, it's not a big deal because I don't use material from the book. I present it in, just collect it from different places, different sources, right? Combine my own way, right? And usually post a note to the Blackboard, right? Which I sent to you yesterday, right? So you should be fine if you just read that. Right? Okay, so, and of course the problems, homework problems are in the mastering physics, so you don't need the book. Right? So what do we have here in problem 14? We have wave, which we know travels to the left. The book says just to the left with speed 2 meters per second. But of course, basically, sorry, it tacitly assumes that you are going to take negative x-axis in that direction. I mean that to the left it means negative x-axis, although I'm not a big fan of these tacit assumptions, right? But anyway, it's not a big deal. All right. Okay, so we have a wave propagating in the negative x direction, right? And some information is given about the wave, this information. So the plot. So we have displacement of the particle, right? Sort of like in a chord. So again, what is d? It's a displacement. So let's say this is our chord, and displacement from the equilibrium 1 centimeters, 2 centimeters. So that's what d is, right? Displacement from the equilibrium, for example, of this point. And so we have what maximum displacement is 6 centimeters, right? And then we have this periodic motion. And we also know that this was recorded at the origin. So that was recorded so it was recorded at x equals to 0. Yeah, and I forgot to write, so this is time and units of seconds. So first of all, before we start solving and everything discussing, we need to realize what type of graph is this. At the end of the video, and of course at the end of my notes, I talked about this because look, this is complicated function of two variables. Our brain is not strong enough to imagine what happens to the wave simultaneously in space and time. It's too much, at least for my brain and for most of people, right? So as a result, in order to simplify the process of analyzing the wave, people usually divide it into steps. First, they can, for example, fix time and see what happens to the wave in space. And that graph is called the snapshot graph, because what happens, how can you freeze time? You take a camera or smartphone, right? And take a picture of the wave. So what happens at that moment when you take a picture? Basically, you freeze time. And then later, 10 years later, you will look at yourself, wow, how thin I was, right? You basically freeze time and you can analyze, right, yourself, right? Or it's a snapshot graph, first situation when you freeze time. The second situation, what if you freeze position, X? It's sort of like you sit, for example, at the origin, right? So wave propagates over here. Let's say this is your origin. You sit here with your watch and you start observing what happens to the wave at this particular point with time. And you record, okay, so it goes up, right? So 5 seconds, it moves up, then goes down, up and down. You don't know what happens at the rest of the points because you fix yourself and you sit at a particular point. So if you plot the graph like that, what we have here, then it's called the history graph, history of this particular point, because you observe what happens with this particular point in time. That's what we have. So I position myself at x equals 0 and observed what happens to that, or what is happening to that point with time. It's a history graph. This is history graph. But of course, when you plot like this, lots of pretty much all spatial information is missing, because you only know one fact, that this was recorded at x equals 0. That's it. So pretty much all the spatial information is missing. We have tons of temporal information, yes, but spatial information is missing. So let me write. This is a history graph. It's a history graph, right? Okay, so and now after these discussions, we can start solving problems. And you know what, on purpose, you see, the problem says the wave travels to the left. But I cannot draw it over here because it's not a snapshot graph. It's a history graph. So we, looking at this, we cannot tell in which direction it travels, right? So that's why I didn't draw a vector showing direction of the wave propagation. But anyway, so now let's start answering the questions. So first we need to answer the question, what about amplitude? Banal question, no discussions. Basically, amplitude, it's a maximum displacement. Maximum displacement you can get from the graph. It doesn't matter if it's a history graph or snapshot graph. Amplitude you can read from the graph, right? So amplitude is 6 centimeters, right? Then part B. What in part B do we have to find? Frequency. df. Okay, guys, be careful. If problem asks or says its frequency, if it says frequency, it means that f. If problem or somebody wants to emphasize on omega, they would explicitly ask for angular frequency. They would never drop this word angular. Right? But if it's just frequency, it's f. So we need to find f, this f, which is the reciprocal of the period. So first of all, to which category that quantity belongs, spatial or temporal? From the definition, basically f, it's a reciprocal of period, so it's a temporal quantity. So temporal quantity, we have lots of temporal information, so we shouldn't have any significant troubles finding frequency. And so if we can find period, then we should be able to find frequency easily, right? Just take a reciprocal. So can we find period? Period, basically, by its meaning, it's a stretch of time over which wave reproduces itself. And that's what we have basically on this history graph. So at this moment of time, at 0.2 seconds, so the wave was here, right? And at 0.8, the wave reproduces its state completely, right? So it means that this stretch of time, it's the period. So if you have a history graph, this distance between troughs or crests, it's a period. But of course, if you have a snapshot graph, you will have plenty of spatial information in a snapshot graph. The distance between crests, for example, or troughs, it will be the wavelength. But here it's a period. So that is our period. So let me show this. So this is T period. So if you have a history graph, period is right in front of you. You can read it from the graph. So period, of course, will be 0.8 minus 0.2 seconds. It will be 0.6 seconds. So, and then of course frequency f, it's a reciprocal of the period. It will be 1 over 0.6 seconds. So it will be 10 over 6, right? Which way I wrote it? Yeah, 10 over 6 seconds. 10 over 6, 10 over 6 seconds. And of course, you can write it as this 1.67 hertz. Right. Wait. I wrote nonsense. You see? Seconds was here downstairs, and then suddenly it jumped. Okay, I can put it like seconds to the power of -1. I can fix it like this. 1 over seconds, that's what hertz is. Okay, so we found frequency. Now, A, B, C. So what is in C? We need to find the wavelength. And again, let's realize which quantity. This quantity belongs to which category? A wavelength, it's a spatial periodicity. Spatial periodicity. And in what is given, spatial information is missing completely. We have tons of temporal information in the graph, but we have nothing almost except for the fact that this was recorded at x equals 0. How can we get information about this, what happens to this wave in space? Because right now it sounds like, oh my God, it's a dead end. We cannot move any further because basically that information is missing. But we need to remember that speed, in order to find speed, you need to mix both quantities from the spatial world and the temporal world. So basically, speed works as a bridge between these two worlds. And since speed is given, so basically bridge is given. So using that bridge, we should be able to move from this world of temporal quantities to the world of spatial quantities, and we should be able to start finding those, but only through the speed. If the speed were not given in this problem, we wouldn't be able to find anything about the spatial, any spatial information about the wave. But because the speed is given, good, so we can move on, right? Otherwise, we would stuck at this point without being able to find any single information about the wave in space. Right, so let's use a V as a bridge. Let me emphasize on that. As the bridge between, okay, so so it's a spatial periodicity. It's a spatial periodicity. So in order to move from what is given, lots of temporal information, into the spatial world, we need to use the bridge. Okay, so now, which I would probably use V equals lambda over T. Period we just found. Speed is given, so we should be able to we should be able to solve it for lambda, right? So from here, okay, maybe I can even frame, so this, from here I can get lambda equals to what? V times T? Yeah. Okay, I use frequency, but what a big deal, right? So in my notes, I used a lambda f because f is also found, right? Oh, let me write it. Or a v equals lambda f, right? So from here, lambda will be equals to v times t. From here, lambda equals to v over f. But of course, you will get in both cases exactly the same answer. So v is 2 meters per second, and divided by the frequency, 10 over 6. 10 over 6. Again, why I keep writing instead of 6 seconds? All right, 1 over seconds. So it will be 6 goes upstairs, so it will be 12 over 10, so it will be 1 over 1.2. Then these seconds goes upstairs, these seconds downstairs, those seconds will be cancelled. So we'll get 1.2 meters, 1.2 meters, right? So that's wavelength. So we managed to find the spatial quantity. Then, okay, pretty much at this point, the problem is over. But I was not completely happy because we can find more information about this wave. So I added additional questions, right? So I added additional questions. So, so let me write add additional questions. So that was C. Now let's look at D. Basically, I want to find all these quantities and I want to write the equation, the wave equation. Right. So first, let's find wave number, right? Yeah, wave number. So first K, wave number. You just need to remember the definition. Wave number, it's a spatial frequency, and we introduce it as 2 pi divided by the spatial periodicity, 2 pi divided by lambda. Lambda we just found. Piece of cake. So K equals 2 pi divided by lambda, right? So 2 pi divided by 1.2 meters, so it will be pi over 0.6 meters to the power of -1. Okay, so now we have this K. Now let's find omega. And after that, phi naught, and it will be, we will find everything that we can find. So now E, yeah, omega, angular frequency. So now let's find angular frequency. Again, look at the definition. It's a 2 pi divided by temporal periodicity T. And T we found. So now you see, it's once you get used to these quantities, right, then it's a very, very straightforward. But first you need to spend some time getting comfortable. 2 pi divided by 0.6, so it will be 2 pi divided by 0.6 seconds, so it will be pi divided by 0.3 seconds to the power of -1. Right? Yeah. And so now let me write. So again, amplitude is, yeah, we found. So pretty much we know everything except for the initial phase. And the initial phase is definitely not 0. When is the initial phase 0? When at t equals 0, wave goes through the origin. Only in that situation, initial phase is 0. But in our case, x equals 0, t equals 0 over here, and the wave is not the origin. So definitely that initial phase is a non-zero value. So let's find initial phase, right? So now A, B, C, D, E, F, right? So let's find phi naught, initial phase. Initial phase. And in order to describe how we can find that initial phase, let me write the equation. So y is a, okay, actually in our case it's a D. Book decided to use D, or okay, in my notes I use D. Okay, it's not a big deal. But you know, it's a displacement from the equilibrium of the points I showed to you. Then wave propagates in the x direction, along x direction. So this variable is x. All right, so x t. But if the problem, for example, said wave propagates or travels in the negative, for example, y direction, over here we would immediately use y. If wave propagated along z direction, here we would have z. So be careful. It's a common place for mistakes. Pay attention, right? All right, so amplitude is, I'm going to use probably, yeah, let me write. No, let me write in general, sine kx. Okay, plus or minus. Since the problem says the wave travels to the left, which is our negative x direction, so there must be plus between this term and that term. Again, it's a place for mistakes, but less often, right? relative to this axis of propagation. So then, so plus omega t and plus phi naught. Okay, and now let's try to understand how can we find this initial phase. We have now plenty of information. We have amplitude, we have this, that, right? And we also see displacements of these particles on the graph. So let's just pick one point with a certain x and a certain t, and look at the graph, the displacement. So we will have d, we will have x, we will have t, pretty much we will have everything except for phi naught. Phi naught is a constant. Right, as wave propagates, nothing happens to that constant. So you can use any point, of course, remembering that this was recorded at x equals 0. So you can take any point, and the constant will be the same. So you can use any points on this graph, right? Okay, 5 minutes left. We should be able to finish it. Okay, so let's pick the easiest point. Of course, makes sense, right, to try to use the easiest. And the easiest is when t equals 0. So let's take this point. Okay, let me emphasize. So that is my point which I'm going to use, right? And we also need to remember that this graph was recorded at x equals 0. So immediately, if you take any point from this graph, x equals to 0, right? So x equals to 0, and if I take this point, t will be equals to 0. So as a result, I will have displacement is at this point 3 centimeters. So this is 3. Amplitude is given. This will be 0, 0, and my unknown. You see? Very simple. But of course, nothing wrong if you, for example, take, this point, 0.2 seconds. X is 0 anyway, because for all of these points, x equals 0. But now time, you will have to, you will not have 0, but you will have this 0.2 seconds. And of course, that you have to use omega, right? Displacement will be in that case -6. But anyway, if you solve it, even for that point, you will have exactly the same phi naught. Or you can take a 0.5. It doesn't matter which point you take, you will end up with exactly the same phi naught. So of course, it's better to use the simplest possible, right? Okay, so I don't want to struggle over here, so let me separate it here, and I will write, let's use x equals 0 and t equals 0. But you can use any other point. But this is the easiest, right? And of course, as I just showed, so displacement at that moment, x equals 0 and t equals 0 equals to 3 centimeters. Right. Okay, so using these facts, so let me rewrite that using all these numbers. So I will have 3 centimeters, that's d. Then equals amplitude 6. Right now, we don't have to convert into meters. But of course, you have to make sure that your amplitude and this d are in the same units. But centimeters or meters at this point, it's not a big deal. Right? Then sine k, of course, k times 0, right? Then plus omega times 0 and plus phi naught. Okay, so we're getting that 3 equals 6 sine of phi naught. So sine of the initial phase equals to 3 over 6, which is 1 over 2. And of course, now we can take arc sine, reciprocal of sine, right? So it will be, let me write it here. So phi naught equals to inverse sine of 1 over 2. And that is, I remember by heart, it's a pi over 6. When I was an undergrad student, our professors all the time used angles only 0, 30, 60 degrees, 90 degrees, right? And as a result, I remember all those values by heart. So that's our initial phase. And initial phase must be in radians. You cannot use degrees. It must be in radians. All these terms in this bracket, in this parenthesis, they're all in radians. Okay, so now we can finally write equation describing this particular wave, right? So d as a function of x and time equals to 6 centimeters sine k, where is my k? Pi over 0.6, pi over 0.6 times, and again, every time today I keep, instead of 6, I write s, then times x, then plus, because it travels in the negative x direction, right? Omega pi over 0.3 times t, and plus our initial phase. Okay, so that's our equation describing this particular traveling wave. So if you know the equation of the wave, you can say you know everything about that wave, right? And we finished right at the correct time, right? So you see, it's not that complicated, but you need to get used to these quantities, right? And usually students after by the time of the final exam, most of the students are quite comfortable, right? Minor mistakes, the most typical place for most of the mistakes. Yeah, basically here I already emphasized, right? So pay attention along which axis wave propagates. If problem says z, here must have z, here you must have z. Right? If it's a y, here must be y, here must be y. And then of course here it will be some d displacement, for example, right? Okay, so that's what I was planning to discuss. I will send you one additional solution to one additional problem. I will just scan it and send it to you, where we will have a slightly different situation. Here you see we have a history graph was given, lots of temporal information. The next problem I was planning to discuss where the snapshot graph is given. Pretty much all the spatial information about the wave is given, but nothing about temporal, except for you can know that that particular snapshot graph was recorded, for example, at t equals 0, right? Again, so how can you move and find temporal quantities from that piece of information? Again, using speed. Speed will be given. If speed is given, again, you can use the expression for the speed in order to find temporal quantities if only spatial quantities are given. Okay, so tomorrow is the last lecture, right? So I will first half of the class we will talk about electromagnetic waves. We just move from the Maxwell's equations. It will be just brief. And then I will talk probably about interference, one-dimensional interference. Right?